everyone. I'm Stefanie, this is Johannes.
Hi.
We're both really happy to be here today, and we're even more happy to see that after 2 awesome talks, you still have energy for a third talk, also talking about offline. So today we'd like to share our experiences building an offline capable web application for our clients. And this guy, his name is Lucas. He's also a colleague of us and a former project member. And we captured his priceless face when our client came to us and asked us if we could build an offline capable web application. So we're all developers, and of course it's the developer. When you hear about offline, you think about, oh my gosh, there's going to be data conflicts. How do we synchronize them, steal data, upgradability, and how do we even test this? But of course, we don't want to be overly dramatic. We like to solve some challenges, and we had it out there to have a look at the HTML5 storage technologies and see what's out there for us. And then we thought, maybe it's not a developer's nightmare. Maybe it's actually a nice little challenge to solve. So before we step into talking about what we did for our clients, we'd like to explore a bit what offline actually means for us. So for us, offline is way more than the T-Rex in a Chrome browser. It's not just having no connection at all. It's also having a very poor internet connection. Imagine going on the tube and being connected via GPRS, or just walking around and losing connection to one router and then have a little very short connection losses until you're connected to the next router again. So when we talk about offline, that's all these scenarios. That should cover all these scenarios. And then you might ask yourself, why? Why do we need to build an offline capable web application if we have desktop applications or just have most of the time connections? And actually, it was not just one client that came to us, it was 2, and asked us about if we could build an offline capable web application. And that's the 2 case studies that we would like to talk about today and share our experiences. So first of all, it was Morrison. Morrison is a big supermarket chain in the UK, and they came to our colleagues in the ThoughtWorks UK. And they wanted to go from paper-based ordering to tablet-based ordering. So what they did before, the store managers had a big bunch of papers in a folder walking around the store and checking how many products were still in stock. And then they would update them and place orders based on how many they had in stock. So for that, they wanted to use tablets now. And they didn't want to commit it to a technology at first, so that's why they wanted to build an HTML5 application. And why did they need offline? So a supermarket is not the best place to cover to ensure a good Wi-Fi connection. First of all, it's really big, so they had the problem of having very small connection drops while walking around and losing connection to one router. And second of all, they have big metal shelves, which is also not very helpful with the internet connection. And third, they also had that very big walk-in freezers where they keep all the dairy products in, milk and cheese and that stuff. So they're pretty good at keeping the cold in, but also pretty good at keeping the Wi-Fi out. So therefore, they needed something, and it was more about robustness for their software while placing orders in the store. And the second project we would like to talk about today, that's the project actually the both of us working on right now. It's about a big retail client in Germany, and they have that traveling product testers. So what they do, they specify the products that they want to build, and then usually a couple of their employees take those specifications that they do in our system with them, and they go right to the manufacturer's side. And they take products that they wanted to sell later on right off the production line, sample products, and then they take pictures of them and see if they would fit what they specified in the documentation before. So they take pictures and notes and say if that product should be sold later on and bought. So for that, usually they don't have Wi-Fi connection at all in those manufacturer halls. So they travel, they take the documents with them for they maybe don't have internet connection for about 2 weeks, go back home and want to synchronize those documents with the colleagues that have been working on in this time. So that's the 2 scenarios that we're going to talk about today and how we solved this. And you might ask yourself, how did we do this? Yeah, that's very nice question. And we tried to put this into 3 different steps that we wanted to, that we needed to solve in order to make our application work offline. It's first of all, how do you get your client available offline? So kind of, how do you install your software in the browser? Then the data available offline, of course, and we already heard a bit about this in Patricia's talk. And also data changes. How do we handle those synchronization conflicts?
Okay, so let's start with getting the client offline. So client offline means getting your whole application offline, the whole web application, all the CSS, all the images, all the JavaScript, and all the HTML. And there are 2 technologies how to do that. And the older one and a little bit the simpler one is application cache. Application cache works like this. You specify a manifest file in your main HTML file. And this file says, to my web application, I need this JavaScript, these HTML files, these CSS files, and then your browser will detect that, install that into a separate form of cache, and the next time your user will go to this very page, and independent if you're online or offline, it will serve out of that cache rather than from the internet. This works really fine if you're building a single-page application, but it has a lot of caveats when you're building a multi-page application, and also it's not very flexible. There's one way it's working, and if this way is working for you, like it's actually working for us, use application cache. If not, there is a little bit a more sophisticated thing, and this is called Service Worker. It's created by a guy from Google named Jake Archibald, and this is somewhat like a programmable cache. So you have this Service Worker, and it's a JavaScript file, and it works in the background of any tab which is going to your domain. So independent of how many tabs are open, it's just one Service Worker. And this Service Worker is able to interject HTTP calls coming from your app. So if you do a request, you will go through the Service Worker, and the Service Worker might go to the internet, if there is internet, and just get all the stuff for you, and then it can also put it into the cache. The thing is, you program the thing yourself. So you can reroute stuff, you can read out of the cache, you can invalidate the cache. You're doing all of this yourself rather than the automatic model, which is the model you have with application cache. Depending on what your needs are, choose one of them. Application cache is a bit older. It's supported on most modern browsers. Service Worker is only kind of ready in Chrome. So make your choice and find something.
Woohoo! We're already 1/3 through. So now you may want to know how you get the data available offline. And actually, our colleagues from the UK, the Morrison example, they used web storage to store their data available offline. There are 2 versions of web storage, local storage and session storage. And it's a very easy-to-use key-value storage, synchronous, that makes it very nice. So for them, a big breakthrough was when they thought in terms of when they thought about their updates in terms of commands. So they knew, okay, I want to update this product that has a quantity, a product ID, or whatever, and I need to store this in a queue. So in case I lose connection, I still have that available. For them, they used local storage, and it worked very fine. In our project, we couldn't use local storage, and that basically for 3 reasons. First of all, we're developing for Chrome only, and in Chrome, the local storage has only 5 MB, and that was simply not enough. Our users write specifications, big documents with tables, text, and images in them. So for us, that was simply not enough space. And second of all, as you might have guessed, IndexedDB has indices, so we wanted to place queries on our data. So we wanted to know, for example, give me some specifications that has been written in that from date X to date Y. So we wanted to place those queries, and that was also possible with IndexedDB. Another thing was that actually at the beginning, we didn't use IndexedDB, we used local storage, and at a certain point, our data got messed up. And we asked ourselves why, until we realized how our users use our application. They actually opened our application in multiple tabs, and we were working at them at the same time. And then they were all writing to the same storage, and our data got messed up. So therefore, we wanted something that gives us locking transaction, which IndexedDB gives us. Because with this scenario, our single-threaded JavaScript suddenly became multi-threaded. So yes, that's how we used it. And another interesting point, as we found, was migrations. That was something we didn't really tackle from the beginning, and at some point we had to. Of course, IndexedDB is schemaless, and also we're running Java on the backend. There's no other particular reason for that as the client wants it, and also MongoDB. And of course, they're both technically schemaless, but we're having a schema that lives in our application. So, and we need to clean that up from time to time. So if we have then a migration going on, of course, migration number 42, first of all, what we do when our Spring context starts, we do migrate all the data on our MongoDB. And as soon as the client connects, for us with application cache, we do have a new version then and ship them all of application code. And with this application code, we ship it a migration.js file so that the client then actually can migrate its own data in the IndexedDB. But one more interesting point is that we actually didn't want to write the same migration code in JavaScript and Java. And we wanted to share that kind of piece of business logic. So therefore, we use something called Nasrn. You may know it by Rhino. Nasrn is the re-implementation of Rhino. And that's a Java engine that lets you execute JavaScript in the backend. And that worked really fine for us. That was OK to set up, and now works since we started doing migrations. Yeah.
OK, finally, how do you handle data changes? Data changes can come in two different flavors. And interesting enough, you can both solve them with a gang of 4 pattern done for undo redo. And one of them is the command pattern, and the other one is the memento pattern. And if you're lucky, you can use the command pattern, and that's what the people at Morrison's could use. So how did they do it? Actually, when someone is walking around this supermarket, they will detect, oh, there is not enough muesli at that place. I need to update the order for muesli so I get more muesli. And so they update the order and they press a button. And by pressing that button, they do an action. And this action can be captured into an object, which is then called the update order command. So when you have those objects with an action, you can get a sequence of the actions the user does, and you simply store them in a local storage, or in the local storage in this form. So they just put them into local storage, and whenever an internet connection was available, they sent the command over the wire, and their server had a message processor where they stored the data into the database. It's not really relevant how the message processor looked like. So either you apply the commands to your data and then you have the end state in your database, or you store even the commands and you do event sourcing and only apply the commands on read. But whatever you do, that's a pretty clean way to do synchronizations. So whenever you have the chance in an application where you have distinct commands to do synchronization, I would try to use commands for that, because it's pretty clean. The user has an idea if a command fails, because if you say, hey, I couldn't update that order because there was already someone else who updated the order, they have a connection to the conflict. But unfortunately, our users are writing documents, so our changes look rather like this. So our users are not programmers, so they don't know diffs. So there's really a hard way. They just type ahead, and every change done to the documents is like a letter typed. So this is simply impossible to do with commands, because the only type of command you would have is update a document, update a document, update a document. So this is not something you can work with. So how do you do that? You create kind of your change sets. And you do that by a pattern called memento, which works like, I have a state of my document, and I remember that, memento. And 5 seconds later, there's a new state of my document, and I remember that. And these states can be transferred. So for us, it's 5 seconds. It can be any arbitrary number. You have to choose what is fitting for you. How does that work? So first of all, the user types. And whenever he types, we have an Angular application, but you can do it with everything. It goes through a JavaScript component called repository. And this repository immediately writes into the IndexedDB. So every keystroke the user does ends up in IndexedDB, like in one document, not in a sequence of documents. And then the repository says, hey, something changed in the database with this document, and it tells this information to another component, also written in JavaScript, called the queue. You can name it whatever you want. We call it the queue. And this creates itself something in the IndexedDB, which is like saving the changes or documented the changes done to your database. And in this case, you have an item with a UID, and it's in state queued. So it's waiting to be synchronized. The changes of this document are waiting to be synchronized. And then we wait for 5 seconds. And after these 5 seconds, it will start syncing that document. So it will change the state to in sync. So it knows, OK, this document is currently synced. I should not sync it again if the syncing process takes longer than 5 seconds. And it tells the document repository, go ahead and save that to the internet, because the queue doesn't know about the internet. The queue just knows about changes. And what now might happen, because sometimes the internet is slow, that the user is still typing. So there are still changes, while on the other end, someone is syncing. So it's just queuing it again. So it's queued and in sync at the same time, and the changes currently done will be synced with the next 5-second cycle. So that's all interesting. But I said 5 seconds. 5 seconds is actually not that easy to detect if you have a business application where users write documents, and usually they have more than one document open. More than one document means more than one engine accessing the database. And you don't want to sync on all the tabs you have. So we were thinking like how to do that. Service worker would be a good way to do it, because you only have one per tab. Another way to do it is shared web workers, because shared web workers are like web workers just between all the tabs. So we have a timer in our shared web worker, which at random chooses one tab and says, you do this thing. Every 5 seconds, someone else, or the same, it's just random. The other thing, and Steffi had it in the beginning on one of the slides, when are we actually offline? So don't go for the navigator.offline property on your browser, because in Chrome it just tells you are connected to any internet. That's not helping you. Are you connected to the internet as a whole, but our server is down? That's also offline. Offline is when you can't connect to your own backend. That's like the definition we choose. And our users want to know when they're offline, because it's important if their data are synced or not. So this shared web worker pings our server and says, hey, are you still there? And then the server responds, yes, yes, all the time, or not. And the web worker will tell all the tabs, hey, you're offline or you're online. So the user knows in every tab the state of the application and if it's currently thinking or not.
Yeah, let me quickly check the time. Yep, nice. So yeah. What is it now? Is this building an offline-capable web application a developer's nightmare or a nice little challenge to solve? So as a good consultant, for whatever that means, I'm going to tell you it depends. But I can, we'd like to share you some questions that we asked ourselves that helped us to determine what technology would fit best for our cases and how we determined what it would be worth spending time on or not. So first of all, it's the size of the data. For example, the Morrison example, the local storage was enough for them. And it's, of course, way easier to use something synchronous than having to deal with the whole IndexedDB quirky API. So size of data matters. Also the structure of data. We were really lucky that our data didn't have much dependencies. So, but if you have a lot of dependencies in your data, then you might want to change to a different storage technology. And it also makes sense that your storage technology kind of matches. So we used IndexedDB and MongoDB. It worked really well together. But if you have to use a relational database, you might want to think of something else on client as well. There's something called WebSQL, which is deprecated, and I don't have much experience in it, but that's maybe something you want to consider. Another one is the potential for data conflicts. In both cases, we were really lucky. Our client said data conflicts are not something that should occur often. So usually, the store managers update the products in the store only on their own. So there's no two people standing in the same aisle and updating stuff. And for us also, only one person should work on a document, even though it can happen that that two people work on the same one, but we should only be able to detect the conflict and not have a sophisticated conflict resolution, which you could do here. We are on a level we thought we could show sophisticated diffs or even do auto merging. Browser support is also a big one. Our application was only supposed to run in, or is only supposed to run in Chrome, so we were really lucky. That's not always the case, but there's some technologies that are just not working or not supported by all browsers. And a very obvious one, but a very one that you should remember is the amount of functionality to work offline. For both our applications, not the full application worked offline. Only the core functionality that they really needed was working offline. Another thing is we're now having users for about a year, and there's some more challenges. We only talked about the challenges that we had while implementing the software, but not really what happened after we went live in production. So there's still two challenges that need to be solved, and one of them is the storage management. Our data is way too large to put it all on the client side, so what do we do? What do we do when our IndexedDB is full? We already heard in Patricia's talk, she had a nice slide where she visualized how Chrome manages your storage. So you actually get half of the available, or she had a third. I think that was probably right. A third of the available memory that you have on your machine, and therefore every application gets a maximum of 20%. So what does our user do when they travel for 2 weeks? Of course, they sit in an airplane for a very long time, so they download a bunch of Doctor Who episodes, and then their machine is full. Their available hard drive shrinks, and therefore they don't have much space to have those documents available offline. So this is still a challenge that we're trying to solve. How do we make it easy for the users to decide when they want to have their documents available offline and when can they be deleted, and not just randomly let them delete by Chrome. Another thing is local data versus non-local data, and that is that actually our users, as we saw before, have the application open in multiple tabs. So what they do is they start writing a document, then switch to another document and to another tab, and want to search for what they just added immediately. But as Johannes mentioned before, we have that 5 seconds delay until it synchronizes with the backend, and our search only is placed against the backend. So it's kind of awkward for them that they have to wait 5 seconds until they can search for what they just entered. So what we're thinking of right now is having actually a search that searches not only the backend but also locally, and then merges those results together to give our users a bit better user experiences while using our software. And yeah, that's that's it. Thanks.
Thanks.